So today we're going to look at key gas monitoring and also some case studies and some examples from the field of both online catches of transformers in failure and also offline testing, the diagnostics, as well as some other follow-up testing that you would do to sort of figure out exactly what was going on with one of these transformers. So a lot of companies that I deal with here at Dynamic Ratings, as Randy said, my background from Memphis Light Gas and Water. I spent a lot of time in the transformer shop. I did some breaker work. So pretty much everything in the substation had my hands on at one time or another. Ended up as an asset manager, and there we were primarily a key gas type monitoring company. So when we say key gas, that's usually going to be based around a hydrogen type monitor. So you have a couple of different kinds of these. You have your basic palladium based chip, which would be a hydrogen only sensor. And then we also have several fuel cell member type monitors out there, where you're going to see a percentage of hydrogen, a percentage of acetylene, percentage of carbon monoxide, and maybe a little bit of ethylene in that as well. But basically, hydrogen being our key gas that we're looking for, as it is generated with most conditions or most abnormal conditions that would occur inside a transformer tank. Now, as I branched out and been here at Dynamic Ratings and dealt with a lot of utilities across the world, you see a lot of multi-gas monitors. So this could be a 3, 5, 7, 9 gas. And the big difference between these is the key gas really lets you know that you have something occurring. And I feel like if used properly, can really give you a heads up into the seriousness of this event that's occurring too in real time. And we're going to go over that in some upcoming slides. With multi-gas, we're able to actually go in and do some analysis of these events. So hydrogen, think of as more of just a smoke detector. It's going to say, hey, we've got something going on. And like I said, if the alarms are set up correctly, maybe give you a bit more information on that as to, do I need to get this transformer out of service, or is this something that we need to further investigate? Whereas if I have a non-gas, I can go in and say, okay, I've got this percentage of acetylene to hydrogen to ethylene. My carbon dioxide, carbon monoxide looks like this. And now I can really make a highly accurate diagnosis of what's happening inside that transformer. So the question you really have to ask yourself when you're considering either one of these avenues for your online monitoring is, what's your intention with this data? What am I trying to accomplish with the monitoring that I'm installing? Because I see a lot of companies out there that are going with a multi-gas only. So say we have limited budget and we're going to spend X amount of dollars on monitoring, and they'll go with the multi-gas only at that point. Well, but then they're not really bringing that data or setting alarms in such a way that it's to a huge advantage of them to have that multi-gas present. And one of the main issues I take with this is there's so many other major failure modes of transformers that are being ignored. So, I mean, you have internal tank failures, but also, bushings. What kind of shape are those in? So obviously power factor, tan delta, and capacitance of those would be something we'd have to consider. LTCs are another thing that we would want to monitor. Through faults are a huge thing, as I feel that through faults are one of those things that really don't even get looked at in concerns to transformer health. So really, if you go through IEEE, there's no real guideline saying after this amount of through fault, we need to do this kind of testing. I mean, or to my knowledge, that's not present. And I feel like, once a transformer, you have breakers that tend to slow over time. through fault durations become longer and longer. Certain areas will accumulate more fault value than others, be that the conditions, through a wooded area, elevation, that type of thing. So these through faults, every time that happens, we're seeing some shifting of these windings and also some thermal degradation that we're not necessarily going to see with other tests, outside of maybe a sweep frequency analysis, if we have a comparison. So that's something else that you may want to monitor. I think it would be an excellent idea to go through your transformers and say, hey, take the 5% of your fleet that's seen that highest level of through fault that year, and let's run a SFRA on those when we take them out of service and do our power factor testing. Okay, so everybody does that power factor every 5 or 6 years, and I've seen many events where there was a great deal of mechanical movement of the windings that the capacitance really didn't change that much for power factor. However, blocking had greatly shifted, some bracing had been damaged, things like that, things that would have been a failure had they been re-energized. So these are things to consider, other failure modes that would fall outside of those which would be indicated through multi-gas detection. Acetylene is not always it's not the first indicator of failure. Well, I guess would be the best way to put that. So, what is key gas monitoring? And we kind of talked about this. Singular composite, basically using hydrogen as a primary gas indicator. And that's largely due to the fact that when mineral oil or transformer oil tends to break down, that hydrocarbon chain is formed out, and we tend to generate hydrogen first. And that would be somewhere around 150 degrees C internal temperature. In that transformer, we're going to start seeing this hydrogen and methane production. And hydrogen tends to generate through all of those values, all the temperatures above that. So there's been some studies, IEEE recently, where that hydrogen generation tends to go up or down, but it's always present through all these values. Whereas we start measuring methane, ethane, ethylene, acetylene, or up to acetylene, through the different energy that's being expended, or the different thermal values as they get higher, we no longer see methane, we start seeing ethane, or we no longer see ethane, we see ethylene. But that hydrogen is that constant. So it really provides us a very solid indicator that we have a thermal condition, that be it PD, arcing, overloading, hotspot situation, where we're exceeding that 150 degrees. So at 150 degrees C, we're also going to start seeing some pretty serious degradation of our solid installation systems. So that's kind of the tipping point of where we're starting to take the life out of that transformer, or useful service life. So the nice thing about these is it does come at a much lower cost point than multi-gas. We're talking single gas anywhere from 5 to 10 grand, whereas multi-gas, generally introductory, we're probably going to be somewhere in the $35,000-$40,000 range for lower. So obviously a huge savings, and I think that if we are, and we all are on some type of budget, when cost constraints is a consideration, maybe it should be looked at as to how much coverage can I get with this transformer, outside of just getting oil values. Because I really do feel like the hydrogen will provide you with notification, as well as the multi-gas, that something's occurring. Again, it just doesn't give you that diagnostic ability remotely. You can still go out and take your manual samples and do that. So here's where we were, and I kind of get ahead with myself with these slides. This goes way back to Rogers, when we're looking at how these temperatures, these gases generate. And I think Jim DeCarm's done some work there, which we would see this as a normalized energy index. But either way you look at it, it's either in degrees C or in joules. And we see that hydrogen typically does generate through every temperature. And we see as temperatures get greater, generally we see a greater production of hydrogen being produced. Now, some of the new graphs, and I really should have included that in this presentation you see from IEEE, we would see somewhere in this 350 range, which if we go would be our ethylene values, somewhere around 350. They're saying that we see kind of a dip through this range of hydrogen generation. So it may not be a completely linear generation of hydrogen as we're seeing here in the initial work, but we do see that it is still generated with either graph. But as you can see, methane's coming out about the same point, that 150 that we're going to see, or 77.5 joules that we would see at hydrogen. And then as we get nearer to 250C, that methane production begins to fall off, and we'll see ethane, 350 ethane going to ethylene, and then somewhere around 700 degrees, we're going to start seeing that ethylene breaking down into that acetylene molecule. So this alone, now that we're seeing this, and we pull that DGA reading, and we see, again, remembering that once we're exceeding 150, we're really starting to have a negative impact on our solid insulation system. And of course, the greater that thermal variant goes up, the more damage that's being caused. So once we get up into this 700-degree range, yes, we're totally wiping that solid insulation, which is also affecting clamping strength, exposing us to a quicker failure through faults. But just with this small bit of knowledge, we're able to take a quick look at a DGA sample and understand, okay, what kind of internal temperature with this defect are we seeing? And this is something that served me very well throughout my career, is understanding, if I see a bunch of ethane, I've got a pretty good idea of that what that hotspot temperature is, and as it relates to what I would want to see around 110 degrees C of that hotspot temperature. So I'm that much hotter. So this is a good guide for kind of understanding that. Now, one of the things we've got to understand when we look at hydrogen, if we're doing hydrogen only, it does make a huge difference where that sensor is mounted. Hydrogen tends to be pretty non-homogeneous distribution throughout the oil blanket of that oil, of that transformer. It also is the least soluble of all these gases. So if we see here, we've got hydrogen at 5%, we've got ethylene at 140, ethane at 180. So this is at 50 degrees C. So this hydrogen will tend to make its way out of the oil rather quickly. So if we use Oswald's coefficient, we will find that roughly we have around a 20-to-1 ratio. So if I've got 50 parts per million of hydrogen oil, probably if I have a nitrogen blanket transformer, I would expect to see somewhere around 1,000 parts per million if I was to sample that gas blanket. So when we're looking at manually drawn samples, a lot of that ppm value of hydrogen that we're going to see in those samples is going to relate greatly to, especially when you see additional gassing. Was it a one-off event? Okay, so I've seen PD events or arcing events that, they're intermittent. That's not necessarily something that's constantly occurring. It could be through a certain tap. It could be in a certain load. So these things are, and so if that event had not occurred very recently, and we pull that oil sample, you may see very low levels of hydrogen, especially when we consider that it does tend to make its way out of the transformer, out of saturation in that transformer rather quickly. So again, now we've got to think about, okay, what's my condition in this transformer? Have I got a lot of leaks present? So if we have leaks, we're really allowing that hydrogen to escape to atmosphere. And a great example of that, if you've ever done any DGA for LTCs, and you look at a free breathing LTC, we all know that in arc, we're going to have about 2 parts of hydrogen to every 1 part of acetylene generated during that arcing event. However, if you go to take a sample from a LTC that's free breathing, unless it has operated very recently, you'll find that you have almost no hydrogen present. So that just gives us some idea of how quickly this hydrogen does move across out of the oil and into atmosphere. So one of the things I've been pushing to a lot of my customers, and it's really kind of a different way of thinking, or a exit to how we generally consider doing monitoring, is looking at hydrogen in gas phase. So I've done some testing on this, and several other companies have as well. So it's not just my word, but when we start looking at how quickly that max level of hydrogen is detected. So when we look at these two graphs, this one on the left was a gas phase measurement. We're injecting 5% hydrogen and a nitrogen base. 15 sensors scattered around the gas phase of that transformer, and we can see that somewhere around 1 hour, we're seeing that full return of that sample that was injected. However, when we move to an in-oil measurement, first of all, we see a bit more interference than we would see with the gas phase. But also we see that full saturation time could be out past 50 hours before we see it. So this is also done in a very well sealed, controlled environment. And we all know that if we have transformers, we do have leaks. So that's another thing that's going to factor in. Now, not to say that those drain valves installations aren't effective, because I've got several graphs I'm going to show you some coming slides where there was actually some saves done with these, but it's just something to consider. And again, it's going to go back to how do we set our alarms up, and I think that's the true key to doing this hydrogen monitoring. So another thing to consider is types of valves. So we what type of valve are you going on? So if we have a gate valve on a transformer, or excuse me, a glow valve, which is typical, that also greatly slows down this migration. If anybody that's ever taken a oil sample will tell you, you have to purge off a certain amount of oil before you take that reading. And I have been to several transformers where the first gallon that comes out of it would be pure water. So free water trapped in the trapped in the drain valve. So when we look at glow valves, this gate, or this pass through tends to make it sort of a P trap sort of thing, where hydrogen will not get out as readily as we would prefer in maybe say a gate valve, which would be preferable for drain valve installations. So just something else to consider when we start looking at these total values measured. This is another thing that can affect that response time. So here is I'm sorry, there's a yellow mark in the middle of this, and I don't know where that came from, and it's bugging me now. So here we're looking at the setting our hydrogen alarms. So this was one of the main things I really want to discuss, is how are we alarming on these values? So if we go to total ppm value, and this is how the majority of alarms are set that I've come across in the industry. So if we're looking at from a healthy condition to a condition 1 transformer, so not anything critical, but hey, something could be happening. And honestly, a lot of people I've talked to, they will ignore this condition 1 unless it persists for considerable amount of time. So it doesn't really raise a lot of red flags off the jump. Now, when we go to condition 2, now we're looking at about 700 parts per million to hit that condition 2. And so this was a transformer that failed in service. And we can see on 124, it started gassing. And we see an pretty stair-step increment kind of climb up to the end of the day on the 25th that we see this transformer actually failed at that point. So we had a couple of days notice that we could have gotten this out of service. Now, but that being said, even at failure, we still had not reached condition 2 based on our hydrogen alarm. So if we're setting those alarms to come in based on those type of values, really not taking advantage of the technology as well as we could. So my recommendation has always been rate of change, and you know, rate of change, not just I do a lot of breaker work. I do almost all the alarming I do is equipment compared to itself. And I feel like that's what rate of change gives you with timing, a percentage of change. These are things that let us know that something either electrically, mechanically, physically has changed in that piece of equipment. I just feel like it gives us a lot, provides alarms much earlier in the inception of these problems. And in this case, if we were to say a rate of change at 25 parts per million per 24 hours. So this alarm would come in at any point that during a day that hydrogen value went up 25 parts per million over 24 hours, we would get this alarm. And ideally, I would want to have this alarm at different levels. So a first stage 25 part per million, a second stage 25 part per million. So if we start looking at this increase, and again, we know we have an active arc occurring. So if we're alarming on those 25 part per million alarms, at the end of the first day, we're almost 350 or 250 in rise of these hydrogen values. So now we're looking, that's 6 alarm stages I would have gone through. And that would let us know that, hey, we need to immediately get this thing out of service. That's because not only do we understand with that kind of change that we have most likely an active arcing type event occurring, but also that it is progressively growing worse. So, you know, whereas a low level or it is not, it is continuing. So it's not a one off. You know, again, I've seen events where, say, a lead flashed over to a wall. We get one shot, and that's it. So not an impending failure there, but something that definitely should not be ignored. But again, not something that we're going to go out and yank out of service immediately. But with something like this, yeah, this would be, we need to get this out. So this is a way to use this technology to better, instead of just being a smoke detector saying, hey, you've got a problem, we can also understand the severity of this problem when we look at it from this rate of change point of view. I thought I had inserted another one of these. So here we go. So also for vacuum type LTCs. So another great tool we can use here. As you know, vacuum type LTCs, we shouldn't see really any gassing present in these samples. Samples should come back completely clean. You will see some acetylene occasionally, as certain models of these do have some bypass switches that will generate some 2 parts per million acetylene, which would be normal for those. But I would still recommend, for if I were to use hydrogen monitoring, that we go with that same rate of change, daily rate of change type of alarm, to understand that, again, even with a total ppm and an active LTC, we would get that ppm alarm maybe within a day if it was activating enough, if it was operating enough. But this 25 part per million per day would give us a pretty early indication that we are having some type of failure with one of those vacuum bottles, and allow us to get in and get that look at things that much sooner. Because a lot of times, it's catching these events, be it a breaker, be it a transformer, it's catching them in their early stages that allows us to prevent those in-service failures. So we're not having fires, we're not having emergency switching events. It's always much better when we can actually make repairs on our schedule rather than an emergency type outage. So using this kind of logic, that really gives us that window to get things out and kind of get them fixed on our schedule. So now that we've said that, again, we can't tell everything looking at a hydrogen value. So we're going to have to eventually take a full DGA sample, be that online or through a manual sample, to interpret what's actually happening. And I'm going to get into this part looking at the combustible gas. Also, I want to talk a little bit about carbon monoxide and carbon dioxide, which is something that I've been studying since about 2011, looking at a lot of failures, a lot of transformers perform good, and how that can be used to better diagnose a problem. So starting with the basic of this, if we see these signatures, these particular signatures. So starting upper left, where we're seeing hydrogen generated in about 2 to 1 for acetylene, we're going to see ethylene values somewhere around 10 to 20%, maybe a little higher, depending on involvement and where in the windings this occurred. But this is going to be very indicative that we've had some kind of arcing event within the transformer. So when you see this, you pull a sample and this is the kind of ratios you're getting, something in that transformer has arced over. If we go to partial discharge, we're going to see mostly a hydrogen generator. So hydrogen is going to be our leading gas on this. One other thing I think is important to understand when looking at partial discharge, at least in my experience, it tends to change over time. So, we can have stray gassing in oil. We can have something due to loading, something due to harmonics, some that are producing that 150C that would give us that hydrogen value. True partial discharge tends to grow over time. And that could be in intensity, that could be in actual volume of the windings that are being affected. Or surface area. So I would expect with partial discharge, actual partial discharge, first sample may come back as mostly hydrogen, some low level methane. Maybe if we take another sample some point further on, we're going to see that methane starting to transfer over to ethane. And so those are the ones you truly want to get on top of fairly quick. When we start seeing that transfer into other gases, because there's more energy being used in that partial discharge. And so with that, we're also seeing expanded degradation of our insulation system. And as that grows, it kind of multiplies on itself. So that's what we're really looking for when we see these type of indicators. What kind of action needs to be taken? So if we go to overheated oil, again, we're looking at ethylene leading signature. And if we remember back, now we're talking about something around 350 degrees C. So this could be something in the windings. This could be bare metal connections, a loose connection. It could be an extra core ground causing circulating currents. But we would see something that looks similar to this sample. So the overheated cellulose, carbon monoxide, I don't know that I necessarily agree 100%. I think a lot of this has to do with type of transformer, and we will get into that here in just a second. So we've kind of talked about our arcing signature. So this was one I really wanted to make a point out of. These are two samples that I collected while I was at the utility. One of them was on the left was actually one that I was actually at my utility. The one on the right was a neighboring utility. So when we look at these signatures, very much the exact same signature. And I know they're represented in percentage of gases, which we see that we're double the hydrogen's double the acetylene values. Ethylene is a little higher than, or quite a bit higher than we expected in arcing. But again, if depending on where that happened in the transformer, it's not unusual to see ethylene values. Anything that looks similar to this is definitely been an arc. So both these samples came from transformers which have tripped out of service. We know we've had an arc occur in both of these transformers. So one of them actually was a winding failure. One of them was a primary lead, had actually burnt in half. We can see actually where it arced over to some support structures. So just a little more backstory on this. These transformers both tripped out. As with most trip outs, some more investigative testing was done. It was sent out, and power factor tests were ordered for both transformers. Both transformers tripped the test set out, couldn't get current on it. So we're seeing open winding. Which of course with the burnt lead, yeah. I mean, we do have a open circuit there. So looking through the DGAs, it became pretty apparent, and this is something I'm saying not just in these two, but through many transformers over the years, were CO2 to CO ratios. So CO2 divided by CO. When we look at that ratio for the one on the left, and now this is in the nitrogen blanketed transformer as well. So that's something else that will affect what these ratios look like. So this transformer was running around 120 to 1. Initially, after the event, we're looking at about 2 to 1. So we had seen a huge swing in this ratio, whereas in the transformer where only the lead failed, we only saw about a two drop of 2. So we were at 7 to 1, we're at 2 to 1. Again, so upper limits of these. So there's some talk about that, and I know when DGA first was started getting looked at as a tool for diagnosing transformer health, the samples were drawn mostly out of conservator type transformers. Now you have to remember neither one of these are that. These are both nitrogen blanket. When you're looking at conservators, it is highly unusual to see a transformer at 121. That would be indicative of a problem to me. Generally, that's where that 15 to 1, 3 to 1 rule kind of falls in with conservator tanks. So anything less than 15 to 1, greater than 3 to 1 would be considered a healthy transformer. And I feel like that's where a lot of our carbon monoxide alarms come from. That's where a lot of the ratio alarms come from initially. However, nitrogen blanket, this is not unusual at all. And typically we will see that ratio with nitrogen blanket transformers tends to climb over time. So this was another transformer I had in service. We obviously had some problems here. We can see that at one point we were up to 2 or 3 parts per million of acetylene, hydrogen climbing, or ethylene climbing as high as 575 parts per million. We have hydrogen. We definitely are generating quite a bit, but again, we talk, a lot of that depends on where the sample's being drawn, where's the event happening at, is it a nitrogen blanket or is it sealed well? So we do see values up around 90 at times. And again, I didn't have online monitoring for this unit, but I have a good feeling if I had taken a gas space sample, because I've done it with some other units, you would find that it was quite high, actually. So that was something else to consider. So I think that a hydrogen alarm still would have been very effective in detecting this problem. But as we can see, if we go through this carbon dioxide ratio, well, first of all, let's look at it from traditional way of looking at a DGA sample. So using total ppm of hydrogen, we're still below condition 1 for this transformer. We were right there, right almost to the 100 mark at one point at when the samples were drawn. So again, online monitoring may have revealed something quite different than that. when we look at ethylene values, we now have the transformer that's at a condition 4, which is let's get this. In fact, it's almost double, more than double condition 4. So that's and let's get this out of service immediately kind of thing, which would also be an overreaction for this type of an event. Again, for optimal reliability, I would much prefer that any of these alarms be based on a rate of change. And also, when we take a look at the CO2 CO or carbon dioxide ratio, we see that it had been fairly consistent, but is steadily climbing. Now, this is never going to be a perfectly linear graph, but we can see that we're up and down. And again, highly dependent on temperature. When was the sample taken will affect this greatly. How well was the sample taken, as carbon monoxide tends to escape the atmosphere rather quickly as well. But we can see overall, if we put a trend line this, we do see that we have a pretty steady increase in that ratio. So in my mind, that's indicating to me that whatever the heating is occurring in this transformer, probably not involving a lot of the solid insulation. As we saw before, things where windings or where we're heating a lot of paper all at once, we tend to see pretty sharp drops in this ratio. However, something like a lead or a connection, that type of thing, really not going to negatively impact this, even though we know we had seen temperatures, especially back around this 2005 date, we had seen temperatures, and let me check to make sure. Yeah, so we had seen temperatures up producing acetylene almost. So we are, we're seeing acetylene production occurring here. So we know we have a temperature of 700 degrees C, but yet we're not really seeing negative impact on our paper. So we investigated, and we did find we had a lead that was actually loose, that was causing an overheated fade, which was leading to this generation of gas. So something that's not really going to be a failure if it's addressed, and using that carbon dioxide ratio in conjunction with the traditional combustible gas helped us really get an idea of what we were looking for when we went into this transformer. And I'm going to speed through. So I did some testing on this in the shop, kind of prove some of this out and get to the end of this. So this was where I actually had built this little setup where I could actually heat paper and just heat oil. And we can see that, yes, around 150, we do start getting this hydrogen generation. Didn't really see any before, but this green line is trending this carbon dioxide. So we see that it did drop. Once we exceed that 150 degrees C, we see a steady climb up to 140 C. Once we set our temperature in contact with paper at 150 degrees C, we start seeing a pretty sharp drop in this. Up into here, this was a bad sample, but it was removed from oil, and we see that when we're in oil only, we see that this ratio tends to go up. So this was a case that just came in. I was looking through that I found really kind of tied everything together pretty nicely, I felt like. So if we look starting in 22, acetylene's at 0 this whole time. We also have hydrogen values at 0. So apparently a really clean transformer. But then if we step over to 23, we're going to start seeing we've had 17 parts per million hydrogen, but we have 2 parts of acetylene building up, 30 of ethylene. And as we move through this, we've stepped up to 4 and 92 and 4 and 103, respectively, of each of these gases. So we've got something that has happened in this transformer. Obviously, a very, very hot problem, something severe. But if we look at our carbon dioxide ratio over this event, 20.73, 14.3, 17, 20, 38, 34. So not going down, pretty much staying, even going up a little bit. So right off the jump, we know we have a event occurring that's somewhere in that 700 degree C range. it doesn't appear to be affecting the solid insulation system so much. So we know this is the LTC type transformer. So now we need to do some more testing to kind of determine what's going on. So some offline power factor tests are run, and we see that, yeah, we're looking pretty good here. Nothing's changed in the power factor that much until we go to excitation current. And we can see that we were high, low, high on all our excitation, but running quite a bit of milliamps, 156, 143, 156. However, in the last two tests done this year, we see that in A phase, we've gone from 156 down to 107.1, 126 on C phase, and 143. So now we've got sort of a stair step type excitation current test. So seeing this and knowing that we have an LTC and a reactive type, so we know we have a preventative auto, so a PA in this transformer, and we're really kind of onto the problem at this point. So we've tracked it down to, and again, some other testing needs to be done. So my thoughts on this was possibly a core ground, extra core ground. So I would meg from the core, see where we're at there. I suspect that PA is going to be our problem. And sadly, they did not provide me with a power factor through each test. So my suspicion is this is an odd tap. So that PA would be in series with this testing. And that, so if we've had some type of failure of that PA on this phase of that, then we would see what we're seeing here. I would really need to see some tests on the even taps of this transformer, or test through every tap to have a comparison to see how this excitation currents. So with the excitation test, of course, the more windings we're involved, the higher that voltage is going to be, thus the higher the amperage. I would be curious to see how that changes. And I got a feeling once they do this testing, we'll narrow it down to likely a PA failure, which will eventually is going to lead to a complete failure transformer if not addressed. So that's just kind of a nice walk through how we would take our online sample, our online monitoring, our offline sampling, our additional testing, and maybe take a look at what's going on. How do we get to the root of the problem? So thank you very much for your time, everyone. I'm going to hand this back to Randy, and happy to take questions.
Yeah, thanks very much, Chris. I have a few comments and questions to make. I recently visited California Department of Water Resources in Sacramento, and they mentioned to me they have 80 transformers in service. I asked them, how many of those have online monitoring? And he said between 5 and 10. And so my question is, how typical is that
That is
as a percentage of online monitoring to transformers installed?
so the utility I worked at, we had 180 something transformers. I think we had 25 online, 25. But what's worse than that, Randy? And as somebody that works on this side of the industry now and realizes the value that can be gained from these monitorings, the failures that can be prevented, how many of those do you think they're looking at? That's the question you really, how many are visible? Because you'll find in most monitors are just sitting there. They are not, there's no comms, there's no backhaul collecting anything. So, I mean, it really is frustrating because I've been doing breaker monitoring quite a bit here at DR, but even with the transformer monitor, I mean, so many of these things are small things that are going wrong, things that could be easily fixed in a lot of cases, and definitely things that shouldn't lead to an in-service failure. That if you were looking at that monitoring, you could completely avoid so much of that. Not only that, but your offline testing. I mean, it's just there's so much that could be helped.
Well, that leads me to my next question. What's the difference in terms of effectiveness between offline and online monitoring, or
Online,
periodic testing and online
no,
monitoring?
no, online. Okay, so you've got a couple of types of failures. I mean, you have failures that happen suddenly, and are appear to happen suddenly. And then you have failures that, oh, we've got a sick transformer. Can we nurse this thing along?
Mhm.
Um, so the effectiveness, I can tell you right now, online bushing monitoring, and as removing myself from a sales guy to just using online bushing monitoring, so much more effective. You will catch bushings failing years before offline tests will even reveal there's a problem, because you're testing it at in-service voltage. So that could be 250 kV that we're testing a bush at, as opposed to a 10 kV test offline. And we're testing it at in-service temperatures. So we might be testing offline at 20C, in-service might be 65. So I mean, power factor is affected by both those. You will see those changes. I've seen examples where there were years before before they were noticed in the offline. In fact, bushings have been tested offline because monitors threw alarms for the utility to say, well, there's nothing wrong with this, only to find out there was. So yeah, I feel like the online, if you're using it and you're setting alarms, like we've talked through this whole presentation, if you're
Sure.
bringing those alarms in, those two failures were both failures that happened in service. They didn't have to happen. They don't have to happen. I mean, it was going to fail, but it didn't have to be a fire failure. It could have been, hey, turn this thing off because we're fixing to lose it.
Is there a most severe gas to find?
Most severe gas.
Hmm.
What do
Is
you
there
mean?
is of all the gases that
Oh
you
yeah,
can find in
acetylene,
your oil,
acetylene,
is it
acetylene.
acetylene? But that's
Yeah,
over 700 degrees C. You
yeah,
only
yeah,
notice
yeah.
it then.
So yeah, so when you've got acetylene, we say 700 degrees C. Now I've seen incidents. Well, we just looked at one. That was a PA. I suspected PA. We saw another that was a lead connection. So when you see acetylene in those low values, 2 parts per million,
Hmm.
4 parts per million, that's generally indicative that you got something really overheating. Will fail,
Hmm.
likely something you can fix if you're seeing it that way.
Hmm.
But with every failure event where you've had some type of through fault event that's taken a transformer out, you're going to see a high level of settling. But yeah, I mean, settling definitely being the most amount of energy used to create acetylene would definitely be the biggest fear. But however, again, if you're looking at the gas, if you're looking at monitoring, if you're looking at DGA and you're trending these values, uh, just because something doesn't have acetylene doesn't mean it's okay. And because you do see acetylene doesn't mean we need to scrap it. I mean, there's more to the story than that.